Hello, and welcome to this tutorial on negative exponents, where we have applications to present value discounting. Now, in the previous tutorial, we looked at positive exponents. For example, 5 squared being 25, or 1.1 squared being 1.21. But exponents may be 0 or negative as well. So 0 exponent, as we'll see, actually always will value to 1. So long as the base itself is not 0. So 5 to the 0th power is 1, 1.1 to the 0th power, 1,000,000 to the 0th power is also 1. Negative exponents will give you essentially the reciprocal of what you would have gotten with the positive exponent. So 5 to the negative 2 is 1 over 25. 1.1 to the negative 2 is actually 1 over 1.21, which would evaluate to 0.8264 and digits after that. So we're giving you results less than 1. So let's try to get some intuition behind the exponent of where the exponent is 0. Why does that value to 1? Well, one way to think of it is there's an implicit 1 times at the beginning of this formula. So we said before v to the n is v multiplied by itself n times. So we might say it's 1 times v to itself multiplied v times. So if it's 1 time, then it's equal to v. If it's 0 times, then you're just left with the 1. So when we sort of look at our results going down in exponents, so 5 cubed is 125, 5 squared is 25, 5 to the 1 is 5, and then 5 to the 0 is 1. And notice each time we're being reduced by a factor of 5. So we're actually going to continue with that to sort of think about negative exponents. So let's look at this. V to the n times v is always going to be equal to v to the n plus 1. So in other words, if we have v cubed times v, then that's the same as 3v's times 1v, which is 4v's, so that's v to the 4th. And this is what it would look like numerically using 5. Now we can turn that around and we can say, well, what if we were going the other direction? So vn, given that we had vn plus 1 divided by v, so vn is the same as vn plus 1 divided by v. So that means v to the 3rd is equal to v to the 4th divided by v. And then we could keep going down. V second is v to the 3rd divided by v, v to the 1, v to the 2 divided by v, and so on. And then you can see how that would work numerically. So we see that each time when we're dealing with our 5 as our base, that we're being reduced by that base by the factor of 5. So let's just keep going. The v to the negative 1 then would be v0 divided by v. V to the negative 2 would be v to the negative 1 divided by v. And you see that we're getting these results. 1 over v or 1 over v squared, okay? Or if we're looking at numbers, 1 over 5, 1 over 25. So again, each time we're reducing by a factor of 5. So we can generalize that and say that the next v to a negative exponent is the same as 1 over v to that same exponent as a positive number. So v to the negative n would be equal to 1 over v to the n. And this would be our examples using variables and our examples using numbers. So let's do a finance application with this. So the question is, how much would need to be invested today in order to have accumulated $100 in 3 years if the rate of return is 10% per annum? So we know what we need in the future in 3 years, and we have to kind of come back in time 3 years and say, what is that amount that we have to have? Well, the formula for that is essentially taking this amount we need, f, and discounting or dividing it by 1 plus r to the n, or we can express that with negative exponents. So it'd be f times 1 plus r to the negative n. So if we're looking at our example here, we have $100 and our interest rate is 1.1 and we're coming back 3 years, so minus 3, and that's going to be 75.13 rounded to cents. And so this is what we would see using our calculator. So 1.1, yx to take it to the 3rd power, but we need negative 3rd power. So you use the plus or minus key to switch that, and that'll do properly. multiply that by 100, and you will get 75.13. We could have put the 100 in front if we wanted. And then we round that to 75.13. So does it work? Because we're basically saying we want to have accumulated $100 in 3 years. Well, let's go back to our other formula and say, well, the value in the future is going to be equal to the value in the present times 1 plus the rate to the nth power. So that's the formula that we're using. We're going to take 75 times 1.1 to the third, and we get $100 rounded to the nearest cent. But actually, if we do it on our calculator, we know it's not exactly $100. It's very close to $100. And why is that? Well, it's because we input a rounded number. And remember, I said we shouldn't do that. So we really should have used the store and reclaim to have tested that. But we might do it in this case because maybe, cent is the smallest unit that we could have. And so we would actually be investing that amount, and we'd be seeing that it would be getting us close to our goal. So to think about this more, we have to think about the timeline. So 0 is today, and we're looking 1 year, 2 years, 3 years forward. And we say we've got some amount today, and we want to know what its value is in the future. And we've got a formula to do that. And essentially, using numbers, we're saying, all right, we're taking $1,000, we're going 3 years in the future, investing at 6%, and we're going to get, according to our calculation, 1,191.02 in this case. So that's 6% per year, compounded for 3 years. Now, what if we were going the other way? So we had an amount here, and we want to go backwards. So in that case, we're going to use the negative exponent, or treat n as a negative exponent. Either works. And so we're going from $1,000 minus 3 years at 6%, and we plug that into the formula, and we get 839.62. So essentially, that's saying this is the amount that we would need. That if we went back forward again, we'd get 1,000. So let's look at some other useful operations with exponents that we'll need in the future. Now we're always dealing here with the same base. So we got the same base v, and we have v to the m, and we're multiplying it by v to the n. Well, it turns out that's the same as if we were to take v to the m plus n, okay? And to see why that's true, think about this example. We've got v squared times v to the third power, v cubed, and v squared is 2 v's. This is 3 v's, so we've got 5 v's. So that works. And it works if we look at numbers as well. 5 cubed times 5 squared, 3 5s, 2 5s, or 5 5s. And you can check that out in your calculator. You should get these numbers. Okay. Now, what if we're dividing? So Vm divided by Vn. Well, in that case, we're going to subtract n. Okay. And to see why that's true, say we had v to the fifth divided by v squared. So we got 5 v's up here on top in our numerator, and we got 2 v's in the denominator, and these cancel those, and we're left with 3 v's. So that's v to the third. And we can do that with numbers as well. And if you still have doubts, you can plug it in your calculator and see, yep, indeed, we do get 5 cubed, or 125. Okay, and I should point out this works even when the n is smaller than the m. So we have v squared over v to the fifth. We would have 2 v's up here and 5 down here. We would in that case end up with, well, 1 over v cubed, and we know that's the same as v to the negative third, right? And this shows it in numbers. And again, you should get the decimal equivalent of 1 divided by 125 if you plug that into your calculator. And then finally, one more. If we have Vm to the nth power, so we're taking this whole expression inside the parentheses to the nth power. So we're kind of taking it first to v to the nth power and then taking it again to the nth power. Well, that will be equal to v to the m times n, okay? And to see why that's true, this is a little bit trickier. You take v squared and you're cubing it. Well, v squared being cubed is v squared multiplied by itself 3 times. And each of these v squares are just v multiplied by itself twice. So if we just sort of lay it out like this, we can see visually that there are 6 v's, so it's v to the 6th, indeed, which is 3 times 2. We can do that with numbers, and we can plug that in and verify that we get the answer shown here. So let's summarize. The point here is exponents are not always positive. They can be 0, and in that case, assuming the base itself isn't 0, we will get 1 as our result. So one way of thinking of it is if we're getting 10% returns for 0 years, well, we're not getting anything, so we just stay with our 1. Negative exponents are used in finance to discount future cash flows reflecting their present value. We saw an example of that. Expressions containing exponents with same base can often be simplified, and we showed the example where we're dividing v5 by v squared. We could be multiplying, we could be taking them to a higher power, and we saw examples of all of that. Now, this is a little bit trickier than the earlier tutorial on exponents, so you may want to review some of this. I'll get some more details, and for that I would refer you to this Khan Academy link, Algebraic Expressions with Exponents. And here I would suggest you go through quiz 2. So again, you can try the quizzes and see if you get everything right, and then look for hints or links to videos of things that you find confusing or difficult. So that's it. Thank you for listening.